Thanks, Barkley. Let me add my welcome. Welcome to Bellevue. Welcome to INCOSE's 2015 International Symposium. Whether this is your first symposium or your 21st, we're thrilled that you're here with us to join us as we gather to share, promote, and advance the best of systems engineering. I wish you a week filled with great information exchange, new insights gained, and perhaps more than a few friends, colleagues, met, and connections made throughout the lifetime. For INCOSE, you heard it stated earlier, it started here. It started in Seattle. Dr. Brian Marr articulated common concerns from many of his aerospace clients, the need for more systems engineers, better processes, more high-quality training. In response, 34 representatives from industry, academia, and government gathered in August 1990 in Seattle. From those humble roots, INCOSE was born. Today, it is no longer the National Council on Systems Engineering. Long ago, we became the International Council on Systems Engineering. With 10,000 members worldwide, in 74 chapters, in 32 countries around the world. It's tremendous progress. As we look back and we celebrate those 25 years of progress, it's very important to look forward as well. Last year, INCOSE published SE Vision 2025. Show of hands, how many people have read Vision 2025? Very good. If your hand's not up, it should go up. You should download it from the INCOSE website. It's a tremendous piece. It's an ambassadorial piece for systems engineering. It's an evangelical piece, but it is a challenging piece. And by the way, it's an extremely well-written piece. It doesn't look like it was written by engineers. It looks like it was written for the C-suite. So please take a look. What I wanted to do today is share my impressions, my thoughts of where we need to go. What is systems engineering for the future? To talk about the future, we first have to talk about the past. Where did we come from? Well, there's the good old days of systems engineering. The good old days that put a man on the moon, missiles in the silos, space station in orbit, tanks on the battlefield. If you talk about the good old days of systems engineering, certain concepts keep coming up. You could always find the best of systems engineering in aerospace and defense. They were long-lived systems. They were standalone systems. They were fresh development. They were electromechanical, okay? And change was rare. Well, the good old days were good, and they're long since gone. Those systems may have been complex for their time, but we all wish for that level of complexity today. From that progress came great innovation, great ideas. While the challenges of today have changed, the foundation is still strong. We do not need to discard that foundation, we need to build upon it. We build upon it in pieces like the INCOSE Systems Engineering Handbook. Version 4, released today here at this conference. Be sure to pick it up. Okay. But our foundation is so much bigger than systems engineering. It's systems science. It's systems theory, systems thinking, systems dynamics. We tend to focus on engineering because it's the interventional system, but our foundation is far bigger. If you've been around INCOSE for the last 8, 9, 10 years, well, you can't go to any session without hearing model-based systems engineering. That's true here as well. We have a paper for the track. We have about 20% of the papers here on model-based systems engineering. It's very, very important. For these 8, 9, 10 years, we have framed model-based systems engineering as the transition, the future. We were wrong. Or, to be more correct, we weren't right. Model-based systems engineering is part of the future, but it is neither as revolutionary as we've made it out to be, nor complete enough to solve tomorrow's problems. Model-based does not mean models are new. That's a common myth. Engineers have always worked in models. They were simply secondary, they were in the background, or more often, they were trapped in the gray matter, in the mind of the chief engineer. But the document was king. The single source of truth was the spec. Well, the next myth of model-based systems engineering is documents are going away. Don't throw out your copy of Microsoft Word anytime soon. Sorry to tell you that. Documents are a wonderful communication mechanism to a very, very wide group of people. What this is a change in centricity. Models which were in the background are moving to the foreground. They're far better tools for thinking, for communicating than ever before. Documents which were in the foreground move to the background. Still a good communication tool, but secondary. So if MBSE isn't enough, what's the shape of the challenge? What's the transition? Well, I will tell you that aspects of the new reality, no longer does aerospace and defense have the market cornered on all the best systems engineering in the world. In some areas, I'll go to automotive. In others, I will go to medical device. In some, I will go to aerospace and defense. But if you want the best in systems engineering, there's no longer one domain that has it. It is no longer electromechanical. Our implementation tool of choice today is software. You can argue, is it 50% of the capability, 60, 70? Doesn't matter. It's the glue that holds it together. It's where most of the functionality and the capability lies in today's systems. And standalone? No, we're not standalone. Long ago, we left even interconnected. Now the phrase is Internet of Things or IoT. Sensors on everything, big data. We live in an interconnected world. That is the future. So if we want to talk about the transition that we must make, it's not from document-centric to model-centric systems engineering. That's a part of it. It is from aerospace and defense to energy, to transportation, to rail, to medical, and beyond. It's no longer long-lived systems, it's varied life cycles. Some short as months, some a century and beyond. It's no longer standalone, it's interconnected. It's no longer top-down, it's middle-out, bottom-up. It's no longer fresh design, it's often brownfield or reverse engineering. And change is the constant. The world is not nearly as simple as it once was. If you look at Vision 2025, one of my favorite graphics is this graphic developed by JPL. It denotes 6 challenges, 5 of which every audience I speak with, they can resonate with. First off, complexity is growing. Mission complexity grows every day. And by the way, it's worse than that. The technologies that we deal with are more complex, the solution technologies. That's a good thing. If they weren't keeping pace, we wouldn't stand a chance. But that makes the world all the more complex. I think as systems engineers, we can connect with the statement that, unfortunately, system design still emerges for pieces. We would like it to be from coherent architecture, but that's not the way the world works right now, as much as we may fight that. So our systems are often brittle, difficult to operate, expensive to operate, difficult to test. We lose information throughout the life cycle. When we shift from conceptual design to detailed design, from detailed design to implementation and beyond, we lose information at every step. But it's worse than that. We don't learn. We struggle to learn across projects, even in product line. And fifth, our colleagues in Project Management Institute, I think will agree, and others around the world, sadly, systems engineers do not work and play well with others, at least project managers. Interestingly enough, we're in it for the same thing. We are all here to meet the customer need, but as the systems engineers focus on the technical measure, technical performance, and program managers focus on cost and schedule, we often find ourselves at odds rather than working together to meet that need. Challenging enough yet? Let me make it a little more. I think we have 8 dimensions to our challenge that we need to be aware of. First off, what's the implementation technology? Is it electromechanical, cyber-physical? Is it a human system? Chancellor Katehi will talk to us about one of those in her examples. Is it a system that is driven purely by policy? Is that the implementation technology? Depending upon what you choose, depending upon your systems engineering techniques will shift. Perhaps not fundamentally, but they will shift. What system type are you dealing with? Within INCOSE, we are quite proud that we no longer only speak of aerospace and defense. We speak of rail, we speak of transportation, we speak of medical, we speak of more, but we still almost always speak of product-centric systems engineering. There's more than that. There's in-service, items that are in our infrastructure that must be upgraded in the field. They must stay functioning. There is engineering of services. There's engineering of enterprises. I've heard it spoken more than once that perhaps INCOSE ought to systems engineer itself. Perhaps one day we will, but I'll leave that challenge to Alan. What level are you getting involved in? Is it the component level, the system level, the ever-present system of systems level this day? Are you lucky enough to engineer back into the problem space or get the entire environment? Your techniques shift. What life cycle phase are you injected in? We'll all love to be there at the first day. First day is where the mistakes are made, or maybe they're headed off. But oftentimes we're not in the conceptual phase. Oftentimes we're not even in the development phase. We may get involved because the system is in trouble and we need to help it. Why are you doing systems engineering? There are many out there who only do systems engineering for process compliance. It's required. Well, there are better reasons to come to systems engineering, but there are worse reasons as well. Are you doing it for regulatory compliance? There are certain members of the oil and gas community that have come to systems engineering for one reason and one reason only: Deepwater Horizon. Not the $85 billion or whatever the price tag was for the settlement, but for the fact that executives went to jail over those practices. So they have come to systems engineering for regulatory compliance so that we can give them the best of our practices. Again, we should welcome them, share what we have, learn their lessons as well. Are you doing it for analytical reasons? Are you doing it for innovation reasons? What type of models are you using? Are you doing architectural or physics-based models? What's the degree of complexity you're dealing with? We often talk about the first, static complexity, the number of parts and the number of interacting parts. That one we understand the best. We're not good at dealing with it, but we understand it. How about dynamic complexity? The fact that our systems are changing and the environment is changing. How about non-deterministic systems? Put 3 autonomous vehicles on the road and allow them to interconnect, and you have a non-deterministic system, which our deterministic systems engineering techniques are not necessarily well suited to. How about the complexity of the project team itself, the number of domains required to bring a solution into being, the team size and structure, if you're lucky enough to be co-located, or are you dispersed across nations, across corporations, across cultures? That has its own degree of complexity. And even the project duration, where your budget becomes uncertainty. I would much rather tackle a year-long project than a 10-year-long project. The lifespan of your system. Are you designing a new cell phone that will be in the stores for a matter of months? Or, like Singapore, are you engineering a nation state where your time frame is on 150 years or more? And last, what's the degree of precedence? Are we dealing with something truly unprecedented? Nothing has been done in this area before. Are we perhaps putting up a new class of satellite? Not a new version of a specific satellite, but we've done satellites. Or are we actually doing product line engineering? Are we engineering the 2017 Ford Mustang from the 2016 product line? The point here is, as systems engineers, we often only look at one level, and typically the most complex of all these. But in reality, we have to tune our practices. The systems engineering applied for this shape problem differs for this shape problem, and we need to be responsive to that. We have to be value-centric. So how do we do it? Well, model-based is part of the answer. We were partially right 10 years ago when we began to herald this as the change. But which model-based? If you listen closely, you will hear that we talk about models with interchangeable terms but mean completely different things. Here at INCOSE, we generally talk about the architectural model. That is your one chance to get a hold of complexity. That is where you can embed resilience. That's where you can innovate. But if you talk to those in the product line management, in the PLM community, SimData and beyond, and you hear them talk about systems models, you hear about high fidelity, analytic, often physics-based models. Those are system models as well. So which do we build upon? The answer when you're asked an either-or question is almost always yes. We have to build on both. The question is, what's your level of precedence? What are you trying to do? If I'm building a 2018 automobile from a 2017 product line, then I am far more on the analytical side of the equation because I'm trying to make it more effective, more efficient. I'm trying to inject new performance. but not necessarily a whole lot of innovation. If I'm tackling something completely unprecedented, and I'm beginning in the early life cycle phases, I start with architectural modeling. But they cannot be disjoint. We have to connect them. There is no one model that can do everything that systems engineers must do. Okay, that is a fallacy. It will not happen. However, the detailed analytical models do coordinate with, do hang off of, so to speak, the architectural model. Models in systems engineering is different than model-based systems engineering. As we make this transition, we need to be careful. These are not disjoint things. We have to connect them, and we have to tune our practice to the problem at hand. MBSC isn't enough. I hate to say it, you're going to have to learn the dreaded O word, ontology, okay? Let me simplify that, because even I don't like to talk about ontologies. I like to talk about meta models or schemas or languages. It's not enough to draw pictures. We must agree upon our terminology. Words must have meanings. The interrelationships between those words must have meanings. It's critical to our communication. It's critical to our analysis. Systems engineers sit at the heart of the communication spoke of a project. We have to communicate with stakeholders, with implementation engineers, electrical engineers, mechanical engineers, software engineers, end users, program managers. We're not going to get them to learn one language. We must have a Rosetta Stone with translators that get to the common concepts that we need, but those concepts must be defined. They must be defined so that we can learn and we can exchange lessons, because aerospace and defense and products and energy and medical devices all have their own embedded language. If we're going to share lessons across the systems domain, we have to have an ontology. We have to have Rosetta Stones to translate to and from those concepts. And if we are to unify as one practice, as opposed to disjoint practices, systems is about seeing the whole, not the parts, okay? But yet we often fragment. We often become tribal and separate our technical processes from our SE management, non-traditional domains, model-based. Model-based is not a separate thing. It's the way we do these other things. If we have the ontology, which model-based will drive us to, we have the ontology for systems engineering. That will allow us to take systems engineering to new levels. It will allow us to capture data at a different way. It will allow us to leverage our peers, our colleagues in academia, bring big data techniques, and really learn and really advance in ways that we haven't been able to advance over the last 25 years. We need to make sure that we're not satisfied with the status quo. Now, my friends in academia will tell me, David, heuristics, wizards, that's not really what you want to strive for. You want the underlying theory of systems engineering. And you know what? I agree. I look forward to the day that we have the equivalent of Maxwell's laws for systems engineering. I simply know that I will no longer be on this earth when that happens. That is a long, long journey. We need the next Einstein, and we need an Einstein who chooses to focus on systems. Now, between here and there is something I would like. I think we all remember Clip-It. Clip-It would click on your screen and say, boy, it looks like you're trying to write a requirement spec. Would you like me to help? Well, my Clip-It never said that. He said other things, but he could have said this. That's not overly helpful. But with heuristics, with patterns, we can assess the goodness of design. I'd like an Einstein wizard to pop up and say, hey, Dave, looks like you're trying to achieve 5 nines of reliability. Would you like me to help? Yeah, I would. Thanks. That is a vision that is possible, certainly within my lifetime, certainly within our practicing lifetimes. And we have to change the way we think about systems. We still fundamentally have systems techniques that are designed for custom build from top to bottom. Yes, we talk about reuse. Yes, we talk about commercial off-the-shelf COTS. But other professions have moved to composability, to building with larger building blocks. That is a shift in technique that we must make. We cannot afford to build everything fresh. We also cannot afford the inefficiencies in our current reuse approaches. It's going to require different integration techniques, different design techniques, but we have to face that challenge. Through this, we need to be very, very careful that we enable, not inhibit progress through process and standards. Now, every once in a while, I can get a bad brand here, a bad name, and say, boy, David is anti-process, anti-standard. No, I'm not. However, once upon a time, standards emerged, processes emerged to embed practices that worked. Now they've become predictive. Now, that's not a bad thing. I like the fact that I can plug my USB drive into a computer and have it work. But there are a couple different standards problems that we can run into. First is proliferation. We've done pretty well on the process side. It used to be, would you like a little 632, a little 499, a little 15288? Well, at least we've harmonized on that side. How about representations and data exchange for systems data? Would you like a little IDEF? How about a little UML, SysML? How about a little AP233, a little AP239, a little XMI, a little OSLC? That's proliferation. And that's nothing compared to architectural frameworks. Would you like a little DODAF, MODAF, TAF, FIAF, DAF, NAF? Somebody once suggested I should form the long architectural framework so we can all have a laugh, okay? We need to get it under control. Proliferation where we serve the standards rather than the standards serving us distracts us from the task at hand. The other cautionary note, there's a difference between market-driven standards and marketing-driven standards. Market-driven standards serve the need of the community. Marketing-driven standards serve the need of the individual offering it. It's very dangerous because we exist in a time of learning. If we lock in prematurely to standards, we standardize on today's performance, which is not good enough. To learn, you must go through divergent and convergent cycles. I hate to say it, we got to make some mistakes and learn from them, and have some successes and learn from them and share. That's divergent thinking. The sharing is convergent. Encapsulate that in best practices and standards and processes and move forward. Standards and processes are good things as long as they're used properly. Where are we trying to get? Well, we are deeply obsessed with this transformation. Like the mechanical engineer making the transition from drafting to CAD, we are so obsessed with our transition from document-centric to model-centric that we forget the bigger world. Well, the bigger world could care less how we do the job, just that we do it. Model-based systems engineering and the techniques I've talked about are transformative for us, but they're not disruptive. What is disruptive is model-based engineering. And we, if we do it right, can enable that. That is what will give the customer and the end user time to market, higher quality, lower cost, more options. And why are we critical? Because we are the ones who live at the very front of the life cycle. We are the ones who are eliciting those needs. We are the ones who are connecting those technology domains. If we do model-based right in the context of model-based engineering, we can be successful and enable model-based engineering. Everything that I've talked about so far is about the practice, but there's another part of this. It's us. It's the practitioners. Whether we consider ourselves systems engineers or whether we consider ourselves clinical engineers who are doing a little bit of systems engineers must transition. 20th century systems engineers applying 21st century systems engineering does not work. Now, every industry that I talk to, every organization that I talk to complains about too few systems engineers, and they complain about the bimodal distribution. We either have very senior systems engineers at or past retirement who have wonderful experience, and we have very junior engineers who have the latest techniques but not a lot of experience. The Helix project undertaken by the Systems Engineering Research Center tried to identify what are the characteristics of systems engineers. If I needed to build one, I couldn't go to a test tube, but perhaps if I know their characteristics, I can identify a good candidate systems engineer and then develop them. Well, 2, 3, 4, and 5 are critical. Effective communication, flexible comfort zone, smart leadership, self-starter. But the one here that is fascinating is the paradoxical mindset. And I've got to break some bad news to you. You're weird. I'm weird. That's not news. The fact is, we think differently than others. I am personally convinced that we are born with a systems perspective, and Western education at least does its best possible job of training it out of us. And it makes us specialists in narrower and narrower fields. Now that enables great technology innovations, but it drives the systems perspective out of most people. When we talk to others, we have to remember that we are unique. We are not better, we are unique. We can uniquely hold big picture thinking and attention to detail in tension in our minds simultaneously. There's generally one other class of people who can do that: business leaders. The other people that we talk to may be able to flip between states, but more often, are specialists. We can be both strategic and tactical, analytic and synthetic, courageous and humble. My wife disagrees with both. Methodical and creative. This sets us apart. So if you're looking for the next generation systems engineer, look for someone with those characteristics and then try to introduce them to the discipline. See if they're interested. We also need to recognize that systems engineering is more than that for those of us who choose it as a dedicated career path. Most people will only dabble in systems, and that's okay. We need to assist them as well. We cannot stand pat on where we are today. We must change our skill set. We must recognize our role as the linchpin. These are systems challenges that we must face. We have to lead, generally not from the front, but often from the middle or the back of the pack. That is a harder job. We still must be T-shaped individuals. We must be broad in scope, but we must have specialty. And we have to expand our competencies, particularly in leadership, socio-technical, soft skills. We cannot stand pat. If we are to unlock our potential to truly make a difference in the 21st century, yes, we must change the practice of systems engineering. We must also change ourselves, and we have to have the opportunity to practice. It is still not a given that systems engineering is a valued profession. If it were, our budgets would never be cut and our schedules would never be truncated. That's not the world I live in. I doubt it's the world you live in either. INCOSE and others still need to fight for the value of systems engineering. The wonderful thing is, within the past 3 years, we've had several great studies. The Guide to Lean Enablers, developed by MIT, PMI, and INCOSE, that talks about effective programs and shows the impact of systems engineering. Or the NDIA study, published by Joe Elm and the Software Engineering Institute, that shows statistically valid data, defensible data, in language that engineers can understand on how important systems engineering is, the true impact that it has on a program. We, INCOSE, need to translate that for the program managers, business leaders, C-suite, greater environment, so that we have the opportunity to bring the skills that you have to bear on these problems. If you look at Vision 2025, and I strongly encourage you to do so, you will see a focus on value-driven practices, complexity, technology, architecting, cybersecurity, all these framed in wonderful from-to statements on how we need to evolve to meet the 21st century. For me, this is what I think about when I talk of 21st century systems engineering. It's technology, it's models, it's multiple domains, it is process, it's resilience, it's reuse, it's autonomy, it's people, tools, global environments, etc. The key is, as always, systems engineering is about balance. It's about remembering our heritage while being open to change. It's about the bookkeeping of systems engineering and the creativity, the holistic thought, the innovation. It's about architecture, where we have our framework for innovation and resilience, and it is about analytics, which bring us rigor and evolution and efficiency and effectiveness. It is about the practice, it is about the practitioner, it is about the opportunity to practice. It is about systems thinking, and it is about systems engineering. Whatever we do, let us always begin with the end in mind. The purpose of systems engineering is not process. The purpose of systems engineering is neither specification nor model. The purpose of systems engineering is not even the system of interest, believe it or not. The purpose of systems engineering is fulfilling that customer and stakeholder need in the most efficient, effective way possible. If we will remember that, we are more likely to be accurate in the journey ahead. The world continues to throw us more daunting challenges. We continue to dream bigger dreams. We must continue to innovate so that we can bring a systems perspective, a systems approach to the systems challenge ahead. Only through that can we tackle the wicked problems. Only through that can we continue to explore new horizons. Thank you.